Hello everyone. I'd like to talk about an application that doesn't require a neural net, but that could take advantage of gradient descent in Torch to optimize very efficiently. And that's the problem of inverse kinematics. So for those who don't know, inverse kinematics is where you have some kind of arm that's attached to some point here that doesn't move. But you can rotate the arm around these joints. So the joints here are depicted as the dots. And you can rotate around each joint and try to get closer to some targets. So what we're trying to do is reach this target from the end here. So maybe I rotate around this joint, and then maybe I take this joint here and rotate around this one. So I'm not changing the length of the bones. I got pretty close there. Maybe what I'll do is I'll do one more rotation around this joint here. And looks like I'm going to get pretty close to hitting the target. All right, so the problem of inverse kinematics is to solve for those rotations at each one of these joints so that you can reach a particular target. So I'll show you how to set this up and cast this as an optimization problem where the loss function is the distance of this so-called end effector, the end of the arm, to the target. All right? Now what we need to represent this arm in memory is two pieces of information for each one of these joints. So first we have the offset of the joint with respect to its parent. So that's the joint that it's connected to on the other side of the bone. So we need the relative offset of each joint with respect to its parent. And then we also need the rotation of rotation matrix of everything below that joint. So you notice when I was rotating the joint here at the top, that didn't affect, or that actually affected everything, right? So when I rotated the joint, that affects everything underneath. If I'm thinking about this as a tree where the root is the thing up here. But if I rotate around this joint here, notice that does not affect its parent, the one above it. It only affects everything below it. So that's what's meant by the rotation matrices here. So just to show you about these relative offsets, in this particular example, if I'm using this XYZ coordinate system that I'm showing down here, then I have an offset of 1, 0, 0 from each joint to the next. So the relative offset of this joint is 1, 0, 0. The relative offset of this joint is 1, 0, 0. And the relative offset of this joint is also 1, 0, 0. I guess we could say the relative offset of this joint is 0, 0, 0. That will put it at kind of the root. So we'll say that, okay, this thing is actually at the origin. We could put it somewhere else if we wanted to, but I'll put it at the origin for now. And otherwise, all the bones here, so the bones are the segments between each joint, all the bones have the same length. Now I could change my mind for the initial configuration here. I could actually say, you know what, I really want my my end effector here to have a relative offset of 1, let's say -1, so we're going down in y, 1, -1, 0. So in that case, the initial configuration of the skeleton would look like this, assuming that these are all the identity rotations. That actually makes the bone longer. Now the bone's length is √2, so you have to be mindful of that. Maybe I didn't want a bone length of √2. I'll keep it simple for this example that I'm doing here and make all the bones the same length. So just be aware that the length of the bone is the distance between the joint and the parent joint there. All right, so what I'm going to do now is jump into Python and start to represent all the information about my arm as torch tensors. Okay, so the first thing I'll do is just set up a little bit of boilerplate code here. This is the basically optimization code I had for torch from before. But I'm going to need to add some stuff to define a loss function for this problem. Okay, so what I'll do is I'll make a list of all the offsets here. So I'll say offsets equals, I'll make a list of torch tensors. So I'll say torch dot zeros 3 and then I've got torch.tensor 100, and then I've got that 2 more times there, right? Okay, so those are my offsets. I'm also going to need to represent the rotations. And, you know, there's a lot of different ways to represent rotations, but I'm going to choose to represent them as rotation matrices, which are actually a little bit redundant, but I'll show you how to deal with that in a second. So what I'll do is I'll make rotation matrices, and I'll assume that they're all starting off as the identity matrix here. And in fact, once I know the first 2 columns of my rotation matrix, I automatically know the 3rd column, because if it's a valid rotation matrix, the 3rd column is the cross product of the first 2. So what I'm going to do here is actually just say, I'm going to take just the first 2 columns of the identity matrix, and I'll make one of those for each of the these joints. And actually, I guess I don't need the last one because there's nothing below that. So I'll say, actually, I'll just make one for in this case, the first 3 of them. If I were to rotate around this, it wouldn't really have any effect, right? Okay. So that's all the information I have. But there's actually one more thing I want to do. So the rotations are the things that are going to change, right? So I want to make sure those are differentiable. So if you remember from the last video, I showed you how to do that. I'm going to make all the 6 elements of the first 2 columns of this rotation matrix require a gradient. So I'll say dot requires underscore grad underscore. Okay, so let me just make sure I can run this real quick. So Python torch, just make sure that all runs okay. Good. All right, so I got the syntax all right there. Okay, now what I'd like to do is make a method to figure out what the positions of all the joints are given the rotations and the relative offsets that are there. So I'll make a method called get positions. It'll take those 2 things as parameters. And the first thing that I want to be mindful of here is that, so these are going to be optimized under torch, but torch doesn't know that these are supposed to be rotation matrices. If you remember how rotation matrix works, so here's a little app that I made. A pure rotation will maintain a right-handed coordinate system. So the matrix that describes the rotation has 3 columns which are mutually perpendicular. So the dot product between any pair of columns is 0. Each column is unit length. And the 3rd column is the cross product of the first 2, as I already said. Now we're optimizing in torch over the first 2 since the third one can be fully determined by them. But torch, because it doesn't know it's a rotation matrix, it may actually violate the condition that the sum of these squares of these is supposed to be 1, so unit length, and that the dot product of these 2 is supposed to be 0, so they might not remain perpendicular anymore. So the first thing I got to do is okay, I'm mindful that I've done some kind of gradient steps. I'm going to take torch out of gradient mode for a second, because I'm going to do something that's not related to the gradient descent at all. It's just a projection onto valid rotation matrices. So I'm going to take myself out of gradient mode and fix something up. All right. And so I'll say here, you know, my first step is to fix up the rotation matrices. And so the first thing I'll do, so I'll loop through each one of them. And so the first thing I'll do is I'll just say normalize the 2 columns. And so in order to do that, I would say r divide equals torch.sum r squared dim equals 0. Okay, so I'm going to sum down each column. Keep dims equals true. Okay, so this is, and actually I need to take the square root. Okay, so I normalize the 2 columns. The second thing I need to do, though, is, again, I'm mindful that this column, even if it's normalized, it may not be perpendicular to the first one. So I need to do a step of what's called Gram-Schmidt. Do one step of Gram-Schmidt. Or, I think it's, yeah. Gram-Schmidt to make the second column perpendicular to the first. All right, and so in order to do that, what I'm going to say is, okay, actually, I need to subtract off the projection. So from the second column, I'm going to subtract off the projection of the second column onto the first column. So I don't want any component of the first column to be in the second column. So let me take the projection of the first onto the second. So I'll say that would be here just the dot product, because these are normalized, that would be the dot product between the first and the second column times the first column, right? So I'll write that in comments here. Subtract off projection of second column onto first column. All right, so I figured out what the magnitude of the projection is going to be. Then I multiply that by the first column and I subtract that off the second column. This may not be unit norm anymore. If there was a component, then I need to normalize one more time here. And so now I'm just going to do, yeah, just that one column needs to be normalized. And so I don't need all this mess here, just the one column. Okay, good. So let me just check to make sure that's okay. Okay, one little thing I realized is that I do actually want a rotation matrix for each of these, but I just don't need to make the last one differentiable. All right, so I'll just make all but the last one differentiable. Okay, so I'll just say rsi is equal to rsi dot requires grad. Okay, so now I think I'm all set. So what I can do now is set up the entire transformation. Set up the entire transformation for each joint. So that includes the translation and the rotation. And the way I'm going to do this is by using 4x4 matrices with homogeneous coordinates. And that's just because I like it. It's all in one place. I'll link to some other videos in the description on how to do that if you're a little bit rusty in homogeneous coordinates. But what it boils down to here is I'm going to make a bunch of matrices. I'm going to start them each off as the identity matrix. And I'll make one of those for each of my, joints. And now what I need to do is, okay, the upper 3x3 part of this matrix is going to be the rotation part. So what I'll do is I'll loop through, so I'll say for m r offset in zip m's r's offsets. So I'm going to loop through all of the offsets and the rotation matrices in parallel. And I'm going to basically copy them into each one of these 4x4 matrices. So the upper 3x3 part of each of these 4x4 transformation matrices is supposed to be the rotation matrix. Now, I have the first two columns, but as I said, I can get the third one as the cross product of the first two. So here I'll say M03, the third column, which is index 2. That is going to be the cross product of R first column, R second column, and I believe I need to specify the dimension too. So I'll say dim equals 0. Okay. Now what I'll do, here's where it gets interesting. So the offset is actually going to be the last column of the matrix because that's the way homogeneous coordinates work. So I can actually pack the translation and the rotation into the same matrix here. All right? So that should be the matrices set up. Let me just, I've kind of written enough code. Let me make sure that I can run this real quick. I'll just call this method on what I have so far. So I'll say get positions, offsets, r's. Let me just make sure that I can run this. So let me just do that. Okay, so it is complaining about this torch.sum. Oh, I meant to write, okay, so that was just a syntax problem. I should have said torch.sum of the element-wise product of these two. So I was just doing a dot product. So this is a dot product. That's the length of the projection times the vector. Okay, let's try it again. Okay, one more issue. Oh, I didn't save it. Okay, I saved it. And now we're okay. Okay, great. All right, so the last thing that I need to do is actually apply these matrices in a hierarchy to get the final positions of the joints in world coordinates. And this is where you might want to go back and review scene graphs a little bit, because that explains why I'm going to do things this way. But basically, I'm going to start off with a matrix that's the identity matrix, but it's going to slowly accumulate these matrices from left to right in matrix multiplication. And as I go further down my arm here, I'm going to keep multiplying on the right by the matrix for each of these joints. So I'll start off with the identity matrix. And what I'll do is I will, okay, so I'm going to collect these final positions. And what I'll do is I'll loop through each of these matrices I just made. And I will immediately do what I said I was going to do. So I'll say, okay, my current matrix is equal to torch.matmul. So I'm going to do a matrix multiplication of that matrix on the right by the most recent joint transformation matrix there. And now I can extract the position as simply the last column, the first three elements of the last column of this matrix. That's going to be the position of the joint. So that's just the way homogeneous coordinates work. So I can actually extract the position that way. So that would be, yep, just like that. And at the end, I can return the positions. All right. So let's just see. As a sanity check, these rotations start off as the identity here. If I print the positions, they should be, should be 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 0, right? They should get accumulated as they go down. So go back down here. Okay, must be tensor. Oh, see, the thing is, I'm so used to using NumPy that I accidentally reverted back to that. But they're very similar. Okay, good. So I got 0, 0, 1, 0, 2, 0, 0, 3, 0, 0. Okay, good. That's exactly how these should start off in world coordinates. But now, as I rotate the matrices, those should update. In fact, give me a second. I'm going to make a little method to plot. I'm just going to add some boilerplate matplotlib code to plot this in 3D so it'll be easier to look at. So we don't have to keep looking at the vectors in the console. Okay, so here's my matplotlib code. If I run this, you'll see that here is the arm, and there's the target. Okay. So, oh yeah, and incidentally, I made a target here. So right now I'm saying the target is 2 in X, 2 in Y, 1 in Z. Okay, so now I'm actually finally ready to go ahead and I'm going to put this into interactive mode, because what I'm going to do is show the process of doing gradient descent in Torch. So I have my Torch loop here. The parameters that I want to optimize over are the rotations, right? So I'm just going to directly pass R's here to the atom optimizer. So those are the things that are actually differentiable that I want the optimizer to tweak over time. But what I want to do now is, okay, so I have this get positions method. I'm getting the positions. I want to create my loss function. And the way I'm going to set up my loss function here is I want to compute the distance between the end effector, so the last position, and the target down here. And so I'll say here, okay, so my distance, that is going to be, and I don't really need, I can do the square distance. It'll be more computationally efficient. So I can say, okay, this would be torch.sum of the square difference between the last position and the target, right? So I got my torch tensor here, that's the target. And I'm going to sum the square differences of the two. If my last position has reached the target, then I'm very happy, and the distance will be 0. All right? So now I'll go ahead and just call this loss, because that's really what it is here. It's a loss function. Whoop. And I think I should be good. The only thing I need to do is, oh, actually, okay, I'll just run this code real quick, and maybe I'll just plot the losses at the end. So maybe I'll put the target in a separate definition here. I'm just going to comment this out real quick, because I'm just going to plot the loss curve at the end to make sure the loss is actually going down. I'll just make sure I'm able to run the code. And let me try that. Okay, so it's running. Oh, I meant to. Okay, everything works great. This is the thing kind of sucks about running Python like this. Okay, good. So the loss curve is going down. It goes down to 0. So give me a second. I'm just going to add this code again here. I'm going to add some boilerplate code to update the thing so that we can actually watch it as it's doing gradient descent. Okay, so what I did here was just uncomment this code up here, and then I added a little code. I said every 10 iterations of gradient descent, go ahead and update the positions in the plot. And so here's what we get when we do that. Okay, so you can see it's moving closer and closer to the target. What I could do here is again, increase the learning rate so that the gradient descent takes bigger steps. Okay, and that actually got there a lot faster. You can see it's getting closer and closer and closer. Something interesting happens though if the target is out of reach. Let's say they put the target pretty far away, maybe 555 here. Let's try that. It can't quite settle down, so it sort of wiggles back and forth, and it never quite gets there. Let me do some more iterations here so we can really watch that. So this is really fun to play with. Yeah, see it's kind of wiggling around. It can't quite, can never quite get to where it wants to be. What it really should do is straighten out. That would minimize the length. Although maybe, is it traveling around a level set here? It might have found a local min. That's interesting. So yeah, if I let's see, if I decrease the learning rate a little bit. Okay, I wonder if it's going to do the same thing eventually, or if it's going to straighten out. No, yeah, it looks like it's going to. Yeah, so if the target is out of range, we got some problems. But let me again give it a nice, easy target that I can definitely reach to, 111. And let's look at that. Well, is this an easy target? I don't know. It overshot it there. Is it going to back up now and eventually settle on that? Oh yeah, and one thing I should do, remember I said, okay, these are supposed to be valid rotation matrices. If they're not valid rotation matrices, it could be stretching or shearing. So what I should do actually is check to make sure that the length between each adjacent pair of joints is actually 1 still. Because that's the way I set this up. They're all supposed to be 1 away from each other. So I'll just do that real quick. I'll say, so my change position, that's going to be positions. Actually, let's see, I already have it in NumPy down here, so I'll just say, okay, so dp equals positions 1 colon minus positions 0 negative 1 colon. And let me just print out, actually the sum of the squares would be enough because it should be 1. So this should keep printing a bunch of things very close to 1. Okay, yeah, good. So the bones aren't stretching too much. I mean, like a little bit, but you know, numerically, they're remaining length 1. So that's good. I tried to put it in an orthographic view here so it wouldn't distort the bones, but I had a little bit of trouble with Matplotlib. I don't think it's doing it properly. So this is not necessarily the best 3D visualizer, but it gives us an idea of what's going on here. Okay, so I hope that was cool, and it showed you again how you can use gradient descent and torch without even really having to think about it. Once you set up your objective function, once you set up your loss function, you could just, you know, do gradient descent. But you know, you might have to do a little more work than we did in the simple median example in the last video. You might have to do a little bit more work to set up your problem, but as long as you know what you're doing, you can always try gradient descent and see how it works. Alright, so that's all I have for now. If I have time, I'll make one more follow-up video where I show maybe multiple end effectors.